In this example, we have an object whose acceleration is a function of position. In this case, the acceleration is equal to 18s minus 5 meters per second squared, and its initial velocity is 0, so it's starting from rest, and its initial position is 10 meters. We want to find the final position when the velocity is equal to 87 meters per second. We know that acceleration is equal to the derivative of the velocity with respect to time. However, in this case, we'll notice that nowhere in what is given do we have anything related to time. So this particular equation probably isn't going to work for what we're looking for. We probably want to use the relationship acceleration ds is equal to velocity dv. In this case, I can just plug in my acceleration into the equation. 18s minus 5 ds is equal to v dv. We'll integrate both sides of the equation, and my limits of integration, when the velocity is 0, my position is 10, and when the velocity is 87 meters per second, my position is s, or s sub f, which is what I'm looking for. So integrating both sides of the equation, I get 18s squared over 2 minus 5s evaluated from 10 to sf is equal to the velocity squared over 2 evaluated from 2 to 87. It's important to remember that we have a velocity as part of this function on the other side of the equation, and that needs to be integrated so that we end up with the velocity squared over 2. Many times students will forget that that velocity is there, and they'll simply write that this is equal to v evaluated from 0 to 87. But this, however, is not correct. Continuing with our problem and putting in our limits, we have 18 times s sub f squared over 2 minus 5 times s sub f minus 18 times 10 squared over 2 minus 5 times 10 is equal to 87 squared over 2. Simplifying this a little bit, we would get 9 sf squared minus 5sf minus 900 plus 50 is equal to 3,785. Further reducing this, 9 sf squared minus 5sf minus 4,635 equals 0. Solving this gives us a value for s sub f that's equal to 22.97 meters, which is approximately 23.0 meters, which is our final answer.